Good afternoon. This is CIVE 634, surface water hydrology, and the class is 092. That's the 9th week, the second class. And I am Professor Victor Ponce from College of Engineering, Department of Civil Engineering, San Diego State University. And the subject today is baseflow, more on baseflow. I've got 3 topics to cover today. The last one is either raster or vector, and I've chosen to do raster, so we're going to do it in video form. However, it's a very long video. It's one of the longest video I've ever produced that are not a class. The classes are 75 minutes, but the actual videos, usually they go 15, 20, 25 minutes, but this one is 48 minutes. It's a long video. So, of course, I encourage all of you to read the raster and, see the video and then watch the material also in vector form, in paper form, in order to, so that you can learn about the material. So we are here, we already covered F01, and I briefly added this F02 Monday because I wanted to briefly discuss, or rather present to you, this very great idea that the people in southern Spain have had for years. I mean, maybe even 50 years. What do they do is this. By the way, I should say that I checked on the web. I believe the record shows that there's about 400 million, if I'm correct, if I read it correctly. Certainly not 40. 400 million trees, olive trees in southern Spain. And they are responsible for large percentage of the global olive oil production. I think it's 30, 40, 50%. It is really amazing. And that is kind of a dry area. It's kind of arid. My guess would be that it rains 500 millimeters over there. So it's in the border between semi-arid and arid. So if it doesn't rain, you could have a drought and it doesn't rain, and then the olive grove would not get any, production. But they have solved that problem. How? By holding onto every drop of water that ever comes into the region. And how do they do it? How do they avoid runoff? This is the way they do it. If you notice, each tree out there, there's 400 million of these trees, by the way. Each tree has a saucer at the bottom. So when it rains, it collects and it gets directly into the roots. That is fascinating and interesting at the same time. They hardly have any runoff in here. And that's why over the years, I believe these olive groves were planted at least 50 years. And they keep adding it to it because the business is very good, right? So that's the way they do it. And I think it's a great system. And it's been recognized all over the world for being very effective way of doing, it's called dry land agriculture, meaning it doesn't rain, but you still can do agriculture and you don't have to irrigate. It is true, though, that a percentage, maybe, I don't know, maybe 15, 20% of the olive groves in Andalusia are irrigated, but they're the minor percentage, the lesser percentage. Okay, so with that, then I am going to do now, I'm going to jump over this because we already covered it in the other class. And I'm going to go, today I'm going to cover F06, F07, and F08. 06 is the theory, which is part of my book. 07 is the practice, and 08 is the video on the effect of groundwater pumping on arid vegetative ecosystems. When I get there, I will give you a little more ins and outs of how is it that I got to produce this work and the video and the related video. So before doing that, I'm going to look at the basics, the theory. And that's done with this link in here, which shows section 11.5 of my book. For those of you, I'm sure that many of you are not familiar with my book because you didn't take surface water. I don't mean that in a bad way, but you didn't take, I'm sorry, not surface water, basic applied hydrology. In basic applied hydrology, I used to cover when I used to teach this, then I was kind of superseded back 5-6 years ago when Professor Kinoshita joined the faculty. She started teaching that because she's the hydrologist person, right? So I was dedicated to other subjects, but my book was organized in 10 chapters that I was going to cover in and out. And then there's 5 other chapters that are for complement, the complementation of my book, because you don't just don't want to do a book that covers only the stuff you're going to teach. So chapter 11 was groundwater, because I felt it was important, even though what I teach in that class is not groundwater. But chapter 11 is groundwater. So in this chapter, we cover, and we're going to look at it, and various subjects that are not really surface water, but are related to baseflow. And baseflow is indeed part of surface water. So we have surface-subsurface flow interaction. That's chapter 11. Then I have 12. Chapter 12 is snow. Chapter 13 is modeling. 14 is, I don't remember right now, and 15 is sedimentation. 14 is just the work of the federal agency. Somebody at the time advised me to write a book, not write a chapter on what are the federal agencies doing in terms of the water agencies. There's 5 or 6 water agencies, actually 5. So I recounted the best work of the Army Corps, the Bureau of Reclamation, the Soil Conservation Service, etc. So this is chapter 11.5, surface-subsurface flow interaction. Is there a surface-subsurface flow interaction in nature? And the answer is absolutely yes. The water from the surface permeates into the subsurface. It stays there for a while. I think I said the other day it was 7 years, more or less, plus minus a few years, give and take. But it actually eventually comes out somewhere. And it's usually within a close range. It doesn't, the water really goes down to the groundwater, which is within a few feet. And then it does an about face. It turns around 90 degrees, almost 90, actually it's not 90 degrees, it's 91 degrees. If it were 90 degrees, it couldn't flow, but because it didn't have a gradient. But if it's 91 degrees, it can flow downstream, right? And that's exactly the way it happens. It turns out, does an about 91 degrees, and it flows as it comes vertically, and then 91 degrees once it hits the groundwater, and then it flows downstream somewhere. Where somewhere? To the nearest, it flows to the nearest appearance of base flow, which could be within miles. It could be 5 miles, 3 miles, depending on the morphology. And suffice it to say at this point that the subject of geomorphology, I consider it to be the most important subject, together with geology. Geology is the origination of things, and geomorphology is the way they ended up for us. Why do I say ended up for us? Because we've been here for 80 years and nature's been around forever. So the geomorphology, as you, not you guys, but the people that are taking sedimentation know that it could take millions of years to form the geomorphology on top of the earth that we are now living in on top of it. So it's very fundamental for us as engineers to understand geomorphology. And while geomorphology is not taught as part of the curriculum of civil engineers, we must learn it as part of your continuing education. And I have done so from the beginning. I was always interested in geomorphology. When I went to Colorado State, I took classes in geomorphology with Stan Shum. I remember I mentioned that. He was a very well-recognized geomorphologist. And since then, I have made it a point to describe geomorphology and incorporate it as part of my professional practice. As a matter of fact, several years ago, I believe it was the year 2014, I wrote a complete paper on geomorphology, covering just about everything that I knew about geomorphology. So it's very important. So, so the geomorphology determines actually the surface-subsurface flow interaction, how deep it gets, and the gradients that are, the gradients are related to the geomorphology. Okay, so there are 3 types of streams. We already talked that, or discovered that, or rather discussed that: effluent or gaining streams, influent or losing streams, and then those streams in the middle, which are intermittent. As I mentioned, like the Gila River in Arizona is an intermittent stream because depending on where you go, sometimes it has water and sometimes it doesn't, even though it might not be raining. So that's a typical intermittent stream. A river that, by the way, I have studied, not extensively, but we have looked at the Gila River and the flows and so forth. The Gila River, it's spelled G-I-L-A, Gila, like that. I guess it should be a local name somehow. It's a tributary of the Colorado. And those of you that are taking my sedimentation engineering class have heard me talk about the Gila River in connection with the floods on the Colorado. So surface runoff and stream flow generation, and I'm going to go rather quick on the topics here because I expect you to read the stuff anyway on your own time and with your own speed. But there's a bunch of ways to generate surface runoff. Hortonian overland flow is the classical one developed by Horton in the middle 30s. Horton is considered to be the father of American hydrology, by the way, Mr. Horton. He wrote a bunch of very good papers in the 30s. Then there's saturation overland flow, which is the stuff that, without talking about it, Marcus used in his methodology. Marcus didn't quite say it, but he did do it. Okay, and then there's other three various processes like through flow processes, partial area, and that are specialized, very sophisticated concepts that basically, I'm telling you off the bat that they're not really used in practice. They're theory and they're part of research. There's always research in any area, right? And then direct channel interception, you have large channels, you could have rainfall falling directly into the channel, for sure. And then finally, surface phenomena. The surface phenomena is something that we particularly have here in Southern California. The surface phenomena includes processes such as crust development, hydrophobic soil layers, and frozen ground. Frozen ground would be in the northern latitudes, about 60, 55, 60, you can have frozen ground for several months out the year. The hydrophobic soil layers are important because they are part of our daily life here in Southern California. Why? Because all the way from south of San Luis Obispo to southern Ensenada, in Mexico, the soil is covered by an ecosystem or a biome that is called Chaparral, or also referred to as Mediterranean ecosystem. Now, this Chaparral ecosystem, we all know, all of you that were born in San Diego or in Southern California know very well what the Chaparral looks like. The Chaparral was here millions of years ago, even before any idea that California was going to be here. So what actually happens is the following, that fire and Chaparral work together. Chaparral burns every 50 years, 30 to 50 years. And it will be a fire, and the fire will produce what is called a hydrophobic soil layer, which, by the way, Professor Kinoshita has made a specialty of this study, hydrophobic soil layers and after fire effects on soils and hydrology, etc. So it's a field, entirely a field of study. So what happens is, as we know, we've studied this also, that the way Mother Nature has designed the Chaparral to survive is that they get covered with a little layer of wax while there is no rain. And sometimes the Chaparral could sustain a couple of years of drought, because there could be a couple of years of drought here in Southern California, and then all vegetation will die. They will not survive a couple of years of drought, but the Chaparral will. The Chaparral goes dormant. It does not evapotranspire because it doesn't have any water to evapotranspire, and it goes dormant. Basically the stomata closes. They close, and it's a microscopic process by which it goes dormant. It goes somehow half dead. And the next time it rains in a couple of years, all of a sudden the thing pops up, and in 2-3 days, where it used to be all brown and bad looking, and now it looks green. So that is the Chaparral. And the Chaparral is our biome here in Southern California, and it is also a biome of 4 places around the world. It's in the Mediterranean Sea. It is in southwestern Australia. It is in southwestern Chile, actually South Chile, the Chaparral, and also in southwestern part of Africa. So wherever there is western exposure in the continents and middle latitudes, so middle latitudes, western exposure, that leads to Chaparral. Then there's only 5 places around the world where you could go out there and look at the biome and call yourself, oh, this looks like my home. Like, this just looks like San Diego, because the vegetation is the same. There's about 5 or 6 species of Chaparral, and there are in all the Chaparral places. But the thing about the Chaparral, as we say, is that it develops the hydrophobic soil layers, and it leads to, after that, it leads to the debris flows. So that's why we have here in Southern California, if we don't manage it properly, and it can be managed in anticipation, but if we don't manage it properly, then it could create debris flows which devastate the country. Typical of this area is the San Gabriel Mountains. The San Gabriel Mountains are rising purportedly about 1 millimeter per year, which is to be the highest tectonism activity in the United States, the largest tectonic activity, 1 millimeter per year. I think that's the right number, but I could be wrong. It could be 10. So don't take me on that figure. You can check it on the web. You can find anything on the web these days. What is the rate of uplift of the San Gabriel Mountains in Southern California? So stream flow generation, hill slope hydrology. I'm not going to get too much in that because this is a lot of theory, but it's good for you to read this because it kind of gets you used to reading about hydrology. Baseflow recession. So this is what we're going to cover here today, and I'm already late on this, but let me keep going in here. Baseflow recession. This is all pretty straightforward, by the way. The truth of the matter is that every time you have a hydrograph, there's going to be two things in here of a hydrograph. And we, like I said, I always say, you guys may not have studied completely in detail all these things, so I'm not going to cover now. I am not going to cover this in retrospect, right? If there's a peak in here in the hydrograph, that means that there was no diffusion, because diffusion diffuses the peak. So this hydrograph over here, which by the way, it's an invented hydrograph, I think. I did it that way. I don't think I took this from any realistic. And then there's a recession curve. There's always a recession curve. Like in here, you have a recession, another recession, a charge, a replenishment of the groundwater. So the water that is flowing under the recession curve is groundwater, and the one on the surface. So surface and groundwater. In the recession curve, there's no peaks because that's operated by a two-dimensional diffusion equation. So since a diffusion equation, there are no peaks. But the ones on the surface, they have peaks because some of them are going through such steep channels that the waves become kinematic, and kinematic wave has no diffusion. We already heard that. And so therefore, you can have these peaks in here. Typically, you have mountain streams that have peaky flows. If the streams are not mountain but valley streams, they don't have peaky flows, the flows that develop peaks. So that's the general form of a hydrograph where we indicate where the recession curves are. And why do we indicate this? Because we are going to calculate the recessions. Now, we're going to do it now. So there's various forms to calculate the recession: 11, 34, 35, 36, and 37. The most common one, the preferred one, is 34 and also 37 by some reason. I'm not quite sure. I guess 37 is also, like I say, established equation. 34, 2. 35 is a deviation, or rather, no, 35 is a modification of 34, but most people don't use 35 because the only difference is that it has the base 10 log as opposed to the natural log E, right? But we use mostly, like I said, 34 or 37, which are the ones that we are going to relate today. So we plot them, plotting these curves, because they're curves in semi-logarithmic paper, with discharge on the log scale yields a straight line because they're logarithmic. And we have a semi-logarithmic, meaning semi means in the ordinates, it's arithmetic, not logarithmic. So then we can show 38 from 33 and 37. There's a straight algebra, which leads to 39. And then you proceed to integrate so you can get to a practical equation, and we get to equation 40. I do believe I remember correctly that I've asked you to go to be Professor Ponce for a minute here and go from 39 to 40. That should be kind of straightforward, but you got to remember your calculus. Okay, so then we get to 41, which is direct integration, combining 34, 38, and 40. And from there, we can do all kinds of things. We can calculate the volume under the recession curve. We can calculate the volume under the recession constant, the volume of the hydrograph under the recession, which is an important point to make. And then we have an example in here, which I urge you to follow carefully, because the homework is going to be related to the examples. So if you follow the examples that I've given you in here, you will be able to do the homework. But be careful because it's not straightforward. You got to spend some time on it, figuring out what to do. Okay, so we calculate the time of storage, the recession constant with the formulas, equation 33, 38, 41, 41, and finally we get the storage, the total storage, which is Q sub O times T sub S, according to this. The equation 41 says Q sub O minus Q, but Q is 0 at the end. So it's Q sub O times T sub S. And Q sub O times T sub S is 8,640 million cubic meters. That's the volume that came under the recession. That's a good number. If the recession indeed gets to touch floor, which it could be, depends, it depends if the entire groundwater is drained and you end up getting a dry river, then you are calculating the entire volume that came under the recession curve. And if it doesn't happen, then you don't have a Q not equal 0, no, a Q equals 0, and that's it. You still can calculate from one point in time to another point in time. Example 11.4 is similar. So I urge you to examine A and B in here, and you start from the flows, and then you can figure out what the base flow is by using these two equations, as we see in there. And calculation of base flow is based on equation 33, and that's basically it. That's basically it. 1100, those are the flows. I just give you the flows, and I ask you to separate the hydrograph into base flow and quick flow. So you got to take a look at the way we did this and proceed accordingly. Now, the bank storage, that's another story that it was interesting. I wrote about bank storage in 1989 because this dates back to 1989. It's exactly 33 years old. Then in the same year, I was hired by PG&E, Pacific Gas and Electric, to study bank storage. And so it was coincidental that I had already done it. So bank storage is like that. The water goes into the storage in the banks, and then it comes back later when the gradient. What does that happen? During the flood, this thing goes up, and as it goes up, it infiltrates into the ground, and then eventually after the flood, it comes down. So that's what we call bank storage. Flood without bank storage and with bank storage. Can you see that? They're stored in here. Diffusion, storage is the same as diffusion, by the way. Storage is the same way. Technically, diffusion is a fancy word that means storage in time. So in here, it's stored without bank storage, then with storage, and then it releases afterwards. Fine, so that's good. And then I have in here some graphs that explain the process. Okay, so we're fine in here, and we are kind of a little bit delayed, but we will try to do the best we can. So now we're coming into regional aquifer parameters using baseflow recession. This is an interesting and fascinating story, by the way. I spent some time in Mexico, well, many times, and this was in the year 1997, I believe, that we went out there and again lucked out because we're able to look at these large rivers and collect data. And I ended up going to a library out there in one of the universities, and it had the most beautiful, complete set of data on the rivers. They had done a tremendous amount of work, and we were able to get some very good hydrograph, which I'm going to show today. So we wrote a paper that was presented various places and so on and so forth. So this paper is going to calculate aquifer parameters by using recession. We're going to use the baseflow recession to calculate the aquifer parameters. Why would we want to do that? Okay, how you calculate aquifer parameters? Well, let's see if we can look at this. No, I can't. So I'm going to go back in here then. There we go. This is not clickable. So it's just, that's the size, but we can increase the size a little bit. There we go. Okay, this is the entire basin of the Papaloapan River. You may have heard of it, you may have not heard. The Papaloapan River is the second or third largest river in Mexico by way of volume. It's a huge river. And it has obviously tributary contributions. It's got a bay out there, and it's got a dam. This blue thing over here is a very large dam that the Mexican government has put together over the years. And got this connectivity in here And this is really kind of a fascinating basin because it's got all kinds of geology, and we'll take a look at that later on. And it also has mountains over here. This is mountainous region. And over here, it kind of ends the mountains and it flattens out. By the time you get over here, it's very, very flat. It's the coast of the Gulf of Mexico. So you got all sorts of things in here in terms of hydrology. There is so much hydrology in here that one of the reports that described the data said that one of these rivers, I don't know which one is it at this point, I don't remember, I have it written somewhere, that the coefficient of runoff was 1.19. Coefficient of runoff. The coefficient of runoff is theoretically the ratio between runoff and rainfall. So it's not supposed to be greater than 1. And yet in here it was 119. So what can you say about that? Well, you can say, oh, well, they made a mistake. They don't know what you're doing. You cannot have a runoff coefficient greater than 1. And the answer is no, the mistake is by the fellow or person that's arguing that, because there is karst geology here. Karst mean limestone geology. And those geologies or geological sites are well known for having underground caves and rivers. The Mexican people called these things cenotes. You may have heard of the word. If you guys have visited Cancun by any chance, and a lot of people visit Cancun, it's a good place to go for vacation. Once you get out there, there are all kinds of people trying to show you the cenotes, right? When I was there for the first time in Cancun, since I'm a riverman, well, self-defined or self-anointed river person, when I was over there for the first time, I was in, what is it called? Cancun, next to Cancun. I don't remember the name right now. Yucatan. And Yucatan, exactly. The peninsula of Yucatan. And I was going to be trying to get pictures of the rivers because that's some of the things I do when I go out on vacation. I get to a river, I take a good picture and I post it on my site. You know, that's part of the business of studying rivers. Well, let me say that I went over land for about 100 kilometers and I couldn't find a river. So I said to myself, what the heck happened here? I can't find any river. I can't take any pictures. Later on, I realized belatedly that there were no rivers out there. It was all underground. There were no surface rivers. They were underground rivers. They were connected by the cenotes, which are underground lakes, underground conduits for the flow. So there's nothing wrong about this value of 1.19 for the runoff coefficient in this particular river. It must be a location where you have an underground river connecting one basin with the other. So that is the reason why just doing surface water hydrology may not tell the whole story. It can if it's just regular hydrology, but not if it's karstic hydrology. Karstic hydrology has a way of defying the issues that we normally take for granted in terms of the runoff coefficient being a percentage. You guys know, and I think I've talked about this, that the runoff coefficient, the average global runoff coefficient is around 0.3 to 0.35. But it varies between, according to Leibovich in his book, from 0.02, that means 2%, to 0.93, that is 93%. Leibovich was careful enough, or happy now, not happy, lucky enough to go into the Philippines and measure runoff coefficient 0.93, which is justified by being a recent geology, like a volcano, that had not had the chance of deteriorate or become weathered yet. So it was all rock. And in all rock, it's all have a lot of runoff, and that's why we have a 93%. I personally never seen a 93%. The most I have gotten is 60, 70%. By the way, the Amazon, we did calculate the runoff coefficient of the Amazon. That was an enterprise, an undertaking, and we figured out that it was 51%. The Amazon basin, which covers 8 countries in South America, has a calculated runoff coefficient at Óbidos, where it is documented and measured. Óbidos is in eastern Pará in Brazil, 51% for reference. So why? Because typically, if the average is 33%, like I said, anything greater than 33% is humid, and anything less than 33% is dry. For instance, here in San Diego, we measure runoff coefficients of 10 to 15%, which is standard and normal. San Diego, it rains, but it doesn't rain a whole lot. So that's why below the average. Again, the average is 33%. San Diego has 10 to 15%. Amazon, 51%. The Philippines Philippines, according to Leibovich, 93%. Okay, so what we did in here is that first we looked at the data, and they had a lot of data. The Mexican government engaged between the 40s and 70s in dam construction around Mexico, and they built a whole lot of dams. They needed to do this, and they did it. It was about the same time with the Bureau of Reclamation and the Army Corps of Engineers were building the large dams in the United States. You guys know, and if you don't, by this time you should, that the agencies in the United States that build the large dams are the Bureau of Reclamation, which does it for the purpose of reclaiming land for irrigation and livelihood, and the Army Corps of Engineers, which does it for the purpose of flood control and navigation. But typically, these two agencies are kind of competing with each other. I don't know why, but they do, okay? Even within agencies, they compete, let alone among agencies. So these guys are competing, and whenever the Army Corps, this is a story that was told by the good old man Reisner, by the way, who wrote the book Cadillac Desert, which I read 3 or 4 times back 20 years ago. And then the poor guy kicked the bucket. Young man, by 50, 55, he died. But he wrote that book before he died. And I had a chance to read it. It was a great book, Cadillac Desert. For those of you that are interested in the stories or the history of water use in Southern California, which is Southern California is defined by how it's used, how they use their water. Fascinating. I should tell you a side story here because it merits that in the year 1900, you guys may not be aware of this. In the year 1900, where California was just developed, the people in California were experiencing a lot of droughts, frequent and perhaps severe droughts. Or perhaps they thought that the droughts were severe because they came from Midwest and Eastern United States where droughts don't happen. Like in the Eastern United States, drought happen every 20 years, which is a long time to forget. And besides, they're not that strong. While over here, they were strong. So they complained to the federal government. They said, this place is unlivable. We can't sustain ourselves. And if you don't do anything, we were going to go back to where we came from. And that really got the people in Washington scared because they realized that they were being threatened by depopulating the West. And they said, no, we're going to do something about it. And somebody out there occurred and said, what we need to do is to irrigate it, store water and irrigate, meaning do hydraulics. And that's exactly what they did. How they were going to do that? They, in 1903, Teddy Roosevelt created the Bureau of Reclamation, purportedly to reclaim Western lands. And they're still in operation. 120, almost 19, 20 years, they're still there. They're based in Denver. The U.S. Bureau of Reclamation, the great hydraulic agency of the United States. They did a lot of the hydraulics. They're in competition with the Army Corps, who also does a lot of the hydraulics. I don't want to get into that. But the point is that the Mexican government built a lot of dams, and they had a lot of data because you don't build dams without data. So they gathered a lot of data, and by the time I got over there, they had a collection of all these bunch of data. At any rate, so I picked up all the information, and I was able to write this paper with all that information. The gauging stations, the stream, the latitude, the longitude, the mean annual precipitation. Look at the mean annual precipitations in there. Fascinating, isn't it? From 3,900 at Zacatepec to 354 at Chiquila, Oaxaca. This is very dry. Well, 3,900 is in the lower end of in Valle Nacional. That's the lower end of the state of Veracruz. That's very wet out there. So you can see 10 times variation within one basin. Interesting story. When I was there in one of my trips, when I was writing this paper, I decided to go out there and travel, see the country. And I was there, and I had to go from one place to another, meaning the place where it rains 3,900 to where it rains 300, say 600, 500. And I was really surprised. I was surprised to go from hill to hill, and the vegetation was changing. Not only was it changing from hill to hill, it was changing from aspect to aspect, meaning aspect is the way you look at it, okay? The way you look at it with reference to the sun. Southern aspect, northern aspect, right? Look aspect, if you're not familiar with this term, look it up on the web. Aspect is what it means the way it looks. Good aspect, bad aspect, right? But no, in hydrology, it refers to the way it looks in reference to the sun. And I was telling you that from aspect to aspect, it was changing the vegetation. And I was not at the time an expert on vegetation, but I was keen enough or smart enough to realize the different types of vegetations that there are. So out there you get from very, very wet vegetation to very dry vegetation. By the time you get to 500 and lower than 500, actually 600, the cactuses are already showing up everywhere. So when the minute you see cactus, you're seeing dry area. Okay, so that's the story. One of the stories that my story that I have to tell you. But we should proceed in here because we intend to finish this. So this is one of the graphs that I collected when I was there. We plotted it, and I had Mr. Kumar that was from India in 4 months working with me. He was sent by his government or his agency to do a training at San Diego State, and he was working with me for 4 months. And Kumar wrote 3 papers in 4 months. Everybody at the time that came over to work with me knew that they had to produce, and they wanted to produce, by the way. So this is one of the papers that Kumar put together. I directed it, and he did it. I mean, I gave the idea and everything. I gave him the data, everything. But look at this hydrograph. This is a fascinating hydrograph. Not only it shows the lack of diffusion for the peaks, but it also shows tremendous amount of nice recession over here for the peaks. What does this mean? It means that from February 10 to April 20th, it rained by 3 times, but 3 times. These are 3 little peaks in here, but they were not big enough to put a change or throw a monkey wrench on the recession. The recession continued, unabated, almost unabated. And then over here, it started raining a whole lot, and then changed, and then the rainy season, then it comes back in here. This is only 1 year. It's an annual hydrograph. But we had succession of years. We only plotted 1 year. Succession of years, and I'm going to tell you a story, a good story in about 5 minutes here. I hope I don't forget. But you can put the years in here all of a sudden, and I mean together, and show the variation of the hydrograph at this place, which was, locally it was called Tesechoacan River at Azueta. Azueta is a place, at a location, at a gauging station. Is it put by the Commission of the Papaloapan River in 1972. Okay, so we wrote this paper, and the story I was going to tell you is that, which is not a good story, but it is a story nevertheless. Then when we submitted this paper for publication in a European journal, it was declined. It was never published in that European journal because it was declined. And it was declined because whoever the reviewers were, and by the way, this thing happens. It happens to me many times, okay? I had a batting average of about 0.70 or something like that, which is extremely good, by the way. 0.70 means that 70% of the papers you submit are accepted. Most people have 50 or even 30%. The very, very good journals had a batting average of 10%, meaning you have to submit 10 papers before they publish one. Okay, but the point is that they decline on the grounds that to be honest with you, I don't know exactly. I don't remember. This has happened 20, 25 years ago. But the point that I want to make in here is that I had 3 hydrographs. These 3 hydrographs, I thought it was a beautiful portrayal of what was going on. So I had 3 hydrographs from 3 different places, and I was going to show exactly what I was going to show. As a matter of fact, I wanted everybody to see that I was going to use these recession curves in order to calculate the hydrograph parameters, which I had not seen so nicely in other places. These were very nice, nicely defined and clear. The comment from the reviewers came back is that they didn't see the reason for putting 3 hydrographs in that paper, because this is a baseflow paper in aquifer parameters. So those guys, I don't want to mention names, nor I want to get nasty or anything, but they didn't see the reason or the need to put 3 hydrographs. And I'm telling you off the bat because I happen to be in the know that they could not relate to the hydrographs because those guys don't work with hydrographs. They work with baseflow, which is typically doesn't look like a hydrograph. So at any rate, they killed this paper, but I was able to publish. By that time, the web was going. So I was able to publish this on the web, and it's still published on the web, and people do read it. And this will be there forever, because I am planning to, forever, I mean forever, because I'm, forever is too strong a word, because I'm planning when I retire, before I retire within a couple months, to archive my entire website in the library, the San Diego State Library. So people will be able to consult my work, even when Professor Ponce is not around, which is good, right? So it will be a permanent archive of my entire website with calculators and everything on the web, on the library. The only difference would be that they're running their own servers. So I was just upload to their servers. That's it. We will not be running. I mean, this right now is coming from my server, but my server eventually finalize, I should say, unplug. We will have to unplug we don't know, we're not going to do it immediately, but within a few years, we will have to unplug my servers. But you cannot go, you can go to the address that it's going to be well known so that you can get to the site. And I know many people around the world like my calculators because they find them easy and quick and nice and good. And if my calculator disappears, they're gonna lose. And as far as I know, there are not too many people doing this kind of work at this point. So let me continue on in here because before I run and get sidetracked in here. So we have the aquifer characteristics. We calculated the time of storage, basin constant, and hydraulic diffusivity. Well, how we do that? We did it from these formulas. In here, we have the A is defined. Okay, the T sub S, so we can figure S over T. So that is the S over T is hydraulic diffusivity. The basin constant is the T over S, hydraulic diffusivity. So whatever's left in here, we can get these three and we can get these and figure out the basin constant and the hydraulic diffusivity of freeze. So we can calculate, we can calculate in here the time of storage, the basin constant that comes from the time of storage, and the hydraulic diffusivity. And then we undertook to take a look at the geology because there was going to be variability between the constants that we were generating, the aquifer parameters. So we looked at the geology. Okay, and I know you guys are not geologists, and I'm not geologist either. But I studied when I went to school many years ago, five decades ago. I took 3 geology courses because I was specializing in water, and that was what they said that I should do. So I am knowledgeable, not to say I'm not a geologist, but I'm fairly knowledgeable. So we have in here all this stuff from geology and the field verification. We had to come up with some data, and we figured out what the data was in the field. They had some data over there for transmissivity and for coefficient of storage, from which we, of course, define the hydraulic diffusivity, because T over S is the hydraulic diffusivity of freeze. Remember I talked to you, Freeze and Cherry? Professor Freeze and Cherry, the two. So we actually were able to verify broadly what we had done. So I'm going to summarize what I had said in case some of you guys are confused. We said, we got this data of transmissivity and coefficient of storage, which was originated by pumping tests. The hydrogeologists go out there. If you want to calculate these coefficients, you hire a hydrogeologist, which would go out there to the field and do a sample, a pumping test, and determine the transmissivity and the S coefficient of storage. That can be done with a pumping test. That's what they do for a living. Okay, I've never done it. There's people that do this. They're called hydrogeologists. Okay, professional hydrogeologists. Okay, then once we did that, but let's not forget that they did it at one point in the entire basin, or 2 points. So it's a point data. And then we went and measured the rivers. And from the baseflow of the rivers, for which we had a lot of data, I already told you the data, those 3 graphs that got cut to 1, they wanted me to cut to 1 because they couldn't understand why was I putting 3 graphs in there. They just didn't see it. And then from indirectly, we're going to get the same coefficients, coefficient of storage and transmissivity. But we're going to get it from the groundwater, not from the pumping test. That means from the groundwater is a more veritable, I guess you could say veritable, better, because it incorporates and encompasses the entire basin, not just one point. That's the difference. You see? So we believe that ours is a better method. And by the way, I was not the only one that was doing this. I actually got the procedure from another gentleman that had done it 20 or 30 years earlier. We just thought that we could apply his methodology to our data, which we have a whole lot. So that's the end of this paper. It's an excellent paper. Unfortunately, it did not get published. I'm not complaining. We published 52 papers, so it must have been maybe 15 to 20 papers that we're unable to publish, one of which is this one, by the way. And there's a couple of others that I discuss in these classes that I also was unable to publish. There's a few out there that were not published on the web and were not published anywhere. Unfortunately, they have gotten lost, totally. I don't want to get into details, but they have gotten lost. At this point, they don't exist. Okay, so now we're going to move on to the last paper. And this is a very long, comprehensive paper that I urge you to look at it, because some of it is going to be on the exam. But we obviously don't have time to cover everything in detail. So, and you're graduate students, you're not undergrads. If you were undergrads, I would have to cover everything in detail and explain to you the 2 + 2 = 4. But you're a grad school, a grad student. You're supposed to do this on your own. Be enticed to do it by the professor, which I am, and then do it on your own. So what I'm going to do now is look at the video. But the video is 48 minutes, and I only have 30. So I'm going to jump around in the video as I see fit. I'm actually going to get started. I'm actually going to get started over here. I believe. Yeah.
Developed humans.
Here we start.
For the past century, developed human societies have learned to tap groundwater for various uses. Thus, the question arises, are humans in competition with plants for the groundwater resource? Would excessive well pumping affect the health of vegetative ecosystems, particularly in arid regions where some plants?
By the way, I should tell you that I was hired by the people in East County, Boulevard. You may not know Boulevard, but Boulevard is part of East County. Boulevard is one of the unincorporated areas of San Diego County. You may have heard of Tierra del Sol, which is part of Boulevard. West of Jacamba. Jacamba is more known by most people, but that's out there. It's about an hour's drive from downtown San Diego. Okay, it took me usually an hour to get out there when I was doing work out there. I did work in Boulevard from the year 2005 to the year 2017. So 12 years I worked out there. We did about 12 projects, by the way. Amazing. Every year I would get a project to do out there. So I know Boulevard like the palm of my hand, really. And so we were out there, and we did all the projects
known to rely
which qualified us to do this work.
Solely on groundwater? These are relevant questions because the health of arid vegetative ecosystems is at stake. The latter provide a host of natural services, including carbon fixation, erosion control, wildlife habitat, contaminant filtering, low albedo, and scenic beauty. These services may be impaired by the excessive pumping.
By the way, what you see in there is a stream. You may not recognize it as a stream, but it is a stream. I'm going to try to erase this. I can't. There it is. This is a stream. Why do we know it's a stream? Because the trees on both sides are riparian. This is a riparian. It's an oak, a live oak, which is considered to be riparian. So riparian means on both sides of the river. It's a stream. So when it rains, it flows, and it can flow for at least I would say a couple feet of depth.
Of groundwater.
The question over here, let me go back. The question over here is there groundwater there? The answer is yes, of course, because the live oak trees are surviving only by tapping the groundwater. If if the groundwater were too deep, let's say 30 feet, you can't get, the live oak trees cannot get there, and they would die. That's all there is to it.
Low albedo.
Normal vegetation, not the chaparral, has to have a sustained way of getting water from the groundwater or from rain. If they can't get it from rain, they'll have to get it from the groundwater. That's all there is to it.
And scenic beauty. These services may be impaired by the excessive pumping of groundwater.
So I'm going to go over the types of groundwater because we already seen this.
This is because the flow of water within a rock aquifer is advective through the fractures, typically in a two-dimensional mode.
Boulevard and Tierra del Sol are full of these situations. Rocks, granite, actually, this is granite diorite. Granite diorite, it's a type of granite, but it's full of cracks, and the cracks are big enough to hold water. And right there's a crack. They're all over the place. So how did this happen? Tectonism. How many years ago? I took my friend Monty Marshall out there one day or a couple of days for a visit, and he said 100 million years ago. And more tectonism. There's always tectonism out there. That area is very active from an earthquake standpoint. We know that for a fact. It is kind of close to the Salton Sea. It's within 20 miles of the Salton Sea. And the Salton Sea is a very active region from an earthquake standpoint. The El Centro town out there, you know, El Centro, has considered to have had some of the strongest earthquakes in the United States, excluding Alaska. I believe Alaska has strongest. But in the continental United States, El Centro is very well known, as well as New Madrid, by the way, in Ohio, in the middle between Ohio and Missouri.
At relatively high speeds. On the other hand, the flow of water within an alluvial aquifer is diffusive through the porous media, occurring at much slower speeds than those that could be attained by pure advection. Fractured rock and alluvial aquifers differ in the predominant mode of exfiltration. Fractured rock aquifers feature springs wherever fractures in the water table intersect at or near the ground surface. Springs are related to the
McCain Valley is a fascinating place out there because it's a desert, and yet it has one of the largest trees in California, if not the largest. I can't say it's the largest because I don't have the data, but I know it's so big that it has to be one of the largest. And how is it possible that in a desert, particularly in a desert, when it typically doesn't rain, you can have this huge tree? The size of the tree is measured by the amount of water that it gets. That we know. That fact we know. The largest trees in the world are in the little triangle out there in the northwest corner of California. They're 80-meter high and I don't know, 3, 5, 10-meter diameter. I don't know. I've been there once, but I can't remember the exact number. You guys know. You can drive a car through it. That's the Redwoods, the California Redwoods.
Number, size, and connectivity of fractures. Therefore, they reflect the local geology and tectonic activity. On the other hand, the exfiltration of alluvial aquifers is driven by the local geomorphology as characterized by stream bottoms, surface depressions, gravens, and so on. Fractured rock aquifers exfiltrate through springs. Alluvial aquifers exfiltrate through the baseflow of streams and rivers. The foregoing facts have a significant bearing upon the relation between groundwater and vegetation. Above a fractured rock aquifer, plants will colonize the immediate vicinity of springs, which...
This is a fascinating picture. Here we have the headwaters of the Tijuana River, but it is in the United States. Because the Tijuana River covers, I don't know, I think it's 40% in the United States and 60% in Mexico, okay? And what do you see in here is the stream. There's a stream over here, and there's a stream over there, and these are the headwaters, meaning the top of the basin, meaning the water goes in the other direction. Over here, in the other direction, over here, in this direction. And what do we see over here? Now, there's an elevation difference between here, at least 100 feet in here. So this is lower and this is higher. This is what we call in the stream, riparian. Well, this is not riparian. This is off the stream, off stream. But yet you see vegetation in there because this is an infrared image. And infrared shows everything green shows red. Infrared, I don't know why they call it that way. So we have vegetation in here. a lot of vegetation, which even goes into Mexico because if I'm correct here, yeah, that's correct. Right here is the end of the United States and crosses into Mexico. So this is what we call a linear forest of red shank. And why is it there? Because there's a crack over there. The water's coming through the cracks and feeding the linear forest. How fascinating.
For the most part, are randomly distributed. This upland interaction between plants and groundwater takes place ostensibly in the absence of a clearly defined stream channel. Conversely, in an alluvial aquifer, plants are known to colonize the immediate vicinity of streams where the groundwater is shallowest. This riparian interaction takes place between plants and groundwater in the presence of a stream channel. This infrared image depicts a portion of Tierra del Sol in eastern San Diego County, California. Two branches of Tierra del Sol Creek are shown, featuring a riparian community of coast live oak, Quercus agrifolia, shown in red color, sparsely populated along the two ephemeral stream channels. Also shown on the bottom right is a tightly packed upland linear forest of red shank, Adenostoma sparcifolium, which is fed by water exfiltrating through a fracture in the underlying rock.
This is really, for me, for my field, is really fascinating. I am lucky that I was able to do work out there, because had I not done this work, I would have never been able to learn all this and put it to you guys like this, the way it is. I was very lucky that I did that. The way it actually happened, I don't know, but I was there and I was hired by them. So let's keep moving along in here.
Is a tightly packed upland linear forest of red shank.
Okay, what's the red shank? The red shank occupies 3% by area-wise of the Chaparral in California. Let's say California. I cannot go to Baja California, but in California it's 3%. That's been documented. The people that know the vegetation. Okay, so it's not a common Chaparral species. One of the things that makes it distinctive is that it's taller. The Chaparral species is 10 feet high, while this guy, the red shank, can get to 20 feet high. So it's a giant Chaparral. It is Chaparral? Yes, it is part of the Chaparral species. So it's a giant Chaparral. Suffice it to say that for the Chaparral to get to be giant, it has to have access to water, because if it doesn't, it won't happen, right? That we already know. So this Chaparral, this type of Chaparral, which is called red shank because of its reddish color, grows wherever there are locations either done by geology or geomorphology. Geology would be cracks that allow springs to get through the rock. Geomorphology, if you have a situation where through diffusion, you get it to a low area where water collects, then the Chaparral can grow. I have not seen that, but I know that the Chaparral covers 3% of the Chaparral in California. I've seen it like this, only in Tierra del Sol, linear forest. We call it a linear forest. We gave it that name, by the way, which is a very proper name. Adenostoma sparcifolium, which is fed by water exfiltrating through a fracture in the underlying rock. Ecosystem will in nature, geology, geomorphology, hydrology, and ecology are thoroughly intertwined into a complex web of relations whose sole purpose is to sustain the vegetative systems. Significantly, geomorphology stands out as the glue that effectively ties all the other components together. The role of geomorphology is nowhere more marked than in arid regions, where it determines whether a plant or ecosystem will exist or not. An example of such determinacy is an oasis, a depression where the groundwater comes close enough to the surface to be within reach of the vegetation. In certain places, depending on the local geology and geomorphology, exfiltration may be of such magnitude as to feed small lakes embedded in otherwise desertic landscapes. For instance, this figure shows the Huacachina Lagoon, an oasis near Ica, Peru. Groundwater exfiltrates into this natural depression located within Peru's coastal desert. In the Mojave River. This figure shows the vegetational gradient along a cross-section of the Mojave River Valley at Camp Katy, California. It is seen that different species occupy different levels in the profile. The dimensions of the terraces depend on the proximity to groundwater, which is conditioned by the local topography, that is, by the geomorphology. Vegetational gradients of the type shown in the Mojave River Valley are not restricted to arid landscapes. This figure shows the sequence of Cerrado Campo Gallery forest, which recurs in the subhumid, highly dissected savanna woodlands of Mato Grosso in central western Brazil. The Cerrado, or dense scrub forest, occupies the higher ground, out of reach of the groundwater. The Campo, that is the grassland, occupies the middle ground, subject to occasional flooding. The gallery forest occupies the lower ground, where there is a significant and active interaction with groundwater. In arid climates, surface water infiltrates into the groundwater as it flows over ephemeral streams. In humid climates, groundwater exfiltrates as the baseflow of perennial streams. By definition, baseflow comes from the groundwater. Therefore, the presence or absence of baseflow is a good indication of whether groundwater is exfiltrating to the surface or not. Streams with characteristics in between those of ephemeral and perennial are referred to as intermittent. These streams may have baseflow only during the wet or rainy season. Soils. For example, smaller streams may have quite large peak to low flow ratios, depending on the local geology, geomorphology, and soils. For example, the Piraí River in Santa Cruz, Bolivia, may reach peak to low flow ratios exceeding 1,000 for a few days during the wet season, January to March. Including surface water, Vados water, and groundwater proper. A total absence of baseflow implies a water table below the stream bottom, sometimes at a great depth. In this case, plants do not use surface water. Instead, they send their roots often to great depths to tap the underlying groundwater. These are the phreatophytes documented by Mainzer. In summary, local climate, geology, geomorphology, and hydrology interact to either foster or discourage the development of vegetation. In particular, in semi-arid and arid regions, more often than not, the presence of phreatophytes is an indication of the proximity of groundwater. In these cases, the depth of the water table may vary from a few feet to as much as 50 to 60 feet. The tallest trees on Earth are the California coastal redwoods, Sequoia sempervirens. The coastal redwood is a long-lived evergreen tree, living 1,200 to 1,800 years or more. The species includes the tallest trees on record, measuring up to 379 feet in height and up to 26 feet in diameter at breast height. Its natural habitat is coastal Northern California, particularly in Humboldt and Del Norte counties, where mean annual precipitation reaches 125 inches, the largest in California.
Its natural habitat extends to the adjoining southern coast of Oregon. P3, located in Santa. The widest tree in the world is a Montezuma Cyprus, Taxodium mucronatum, located in Santa Maria del Tule, about 6 miles east of the city of Oaxaca, Mexico. In 2005, its trunk had a circumference of 137.8 feet, which represents a diameter of 43.9 feet. The best estimate for the age of this tree, based on growth rates, is 1,433 to 1,600 years. The tree is located near the center of a narrow valley between two hills within the confines of the broader Valley of Oaxaca. The mean annual precipitation in the area averages 746 millimeters, a bit less than the global average, 800 millimeters. Therefore, the ample moisture that sustained this remarkable tree must originate in local groundwater from the nearby hills. All vegetation responds readily to moisture inputs from all sources, including surface, soil, groundwater, and air. Absence of water is definitely limiting. On the other hand, ample water leads to trees of great size, such as the California Redwoods. Too much water may lead to a dearth of nutrients due to soil leaching through geologic time. However, large tropical forests, such as the Amazon, are able to store nutrients in their extensive canopy and recycle them as appropriate. The preceding examples have shown conclusively that the presence of water has a direct bearing on the physiognomy, that is, height and density of vegetation. This fact is nowhere clearer than in a desert landscape, where the size differences may be attributed to the prevailing gradient in the depth to the water table. For instance, Brown, in 1923, has documented the height of mesquite, Prosopis species, between two wells located in the Coachella Valley near the Salton Sea, California. Mesquite grows as a dense forest 10 to 25 feet high along the eastern well, and of somewhat less size, 6 to 8 feet, on high sand dunes to the west. Within a distance of 2 miles from east to west, the depth of the water table increases from 32 feet to 75 feet. Ostensibly, mesquite does not grow beyond a depth of the water table of 50 feet. In fracture rock aquifers, the influence of moisture availability on the height and density of vegetative ecosystems is confirmed by the existence of linear forests, or lineament. This figure shows a remarkable linear forest of tall red shank, Adenostoma sparcifolium, in Tierra del Sol, San Diego County, California. This forest is fed by water exfiltrating through a linear fracture in the underlying rock. Downstream edge of the large dike shown on right. Land subsidence, for instance, water table depletion, progressively making it harder for all users of the aquifer to pump groundwater. Loss of wetlands, including possible impairment of oasis, phreatophytic, and spring-fed vegetation. Loss of baseflow and riparian corridors, which may trigger changes in channel morphology and lead to stream bank erosion and increased sediment loads. Land subsidence, for instance, see the Las Vegas experience. Saltwater intrusion in coastal environments. It is clear that both plants and wells pump groundwater. This fact has been amply confirmed by theory and experience. The two systems, one natural, plants, and the other anthropogenic, wells, when located in close proximity of each other, are actually drawing water from the same reservoir. Therefore, the question arises, are wells in competition with the plants for the groundwater resource? If well pumping results in a lowering of the water table within reach of the roots, the answer is an unequivocal yes. Lowering of the water table as a result of pumping will encroach upon the livelihood of many desert vegetative species. The mesophytes will be particularly affected since these typically require substantial amounts of water. The latter flows in springs and under depressions, following paths established by local geology and geomorphology. Filtering of contaminants, low albedo, which encourage it to be slow, with recharge events few and far between. Groundwater pumping may not be as crucial in a humid environment because in this case, surface water may be plentiful, largely eliminating the need for pumping. A middle ground may be found in the relatively new concept of sustainable yield. The amount of groundwater capture should not be based on the outdated hydrogeologic principle of safe yield. Instead, the allowable capture must be that which can be maintained for an indefinite period of time without causing unacceptable environmental, economic, or social consequences. These consequences would have to be carefully evaluated and accounted for in the economic analysis before the planned groundwater development takes place. The latter requirement calls for renewed interdisciplinary syntheses in groundwater resource evaluation to include ecology, surface water hydrology, and the economics of natural resources. The following conclusions are derived from this study. Climate, geology, geomorphology, and hydrology interact to foster or discourage the development of vegetation. Many plants in arid and semi-arid regions rely almost exclusively on groundwater to satisfy their basic need for water. The presence or absence of water has a direct bearing on the height, width, and type and density of vegetation. The concept of safe yield of groundwater has been widely discredited because it assumes that groundwater is a volume when in fact it is a flow. In a pristine groundwater system, gross recharge equals gross discharge. Therefore, net recharge is zero amount of fossil fuels, thereby increasing the carbon footprint. Usage of groundwater must be exercised with caution, anticipating the impacts that it may have on local stakeholders, both natural and anthropogenic. The allowable groundwater capture must be that which can be maintained for a reasonable time without causing unacceptable environmental, ecological, economic, or social consequences. There is an urgent need for renewed interdisciplinary syntheses in groundwater resource evaluation to include ecology, surface water hydrology, and the economics of natural resources. We obviously, a couple of years ago, 3 years ago, we spent a lot of time, Jana da Silva, who was a student graduated in the year 2020, right as the pandemic got started, produced this video, of course, with my help and my assistance and my direction. It was, as I said, the longest time-wise video, academic video that we have produced, other than virtual lectures, which go on for
60 to 75 minutes. So thank you very much. Today is Wednesday. I will see you next Monday at 5:30 as usual. Thank you.